Tagging an asteroid. NASA did it. I'm Tonya Hall, and joining me is Dr. Dante Lauretta, professor of planetary science in the Lunar and Planetary Lab at the University of Arizona and principal investigator for the NASA OSIRIS-REx asteroid sample return mission. Welcome, Dr. Lauretta.
Thanks, Tonya. It's great to be here.
Back in July, we spoke to you about the OSIRIS-REx spacecraft meeting up with asteroid Bennu about 200 million miles away and snatching a sample of the surface material for transportation back to Earth. Well, that meeting just took place. Tell us about it.
On last Tuesday, October 20th, the OSIRIS-REx spacecraft descended down to the surface of asteroid Bennu. It was an absolutely flawless operation. I'm incredibly proud of the team. The spacecraft contacted the surface very close to our targeted point, well within 1 meter of the predicted location. We contacted the surface with our sample collector, which is kind of like this circular filter device. We observed it push down into the asteroid regolith, which is what we call the loose material on the surface. So it was the best position we could have gotten at. We fired the gas, which is how we drive the sample into the collector chamber. We saw lots of material moving around. It was a very dynamic interaction. And we backed away safely from the surface after over 9 seconds of moving forward into the asteroid surface. So we actually pushed down pretty deep, at about 50 centimeters down into the soil on the asteroid.
The sample collection was so successful, in fact, that we picked up a little more material than we planned. How are we managing that?
Yeah, one of the things we did right away was we brought the sample collector into the field of view of one of the cameras, the SAMCAM. And it was quite a shock to me, actually, as those images were coming in, because we could see particles radiating away from that collector mechanism. And we did a lot of analysis on what was going on, and it turns out we did almost too good of a job. Our bucket is full of asteroid sample, and we're in this microgravity environment, so every time we move it, it just sloshes like a fluid. And a little bit is flipping over this lid and escaping into space.
What challenges were involved in having the spacecraft match the speed and direction of the asteroid for the sample maneuver to succeed?
Definitely one of the greatest challenges of the mission was getting the spacecraft into the right position, moving at the right speed relative to the asteroid surface. It was a delicate set of maneuvers that got us into that proper attitude, and a real testament to the hard work of the team. We ended up, because the spacecraft is so far away, we're over 200 million miles from Earth as we were performing this operation. The one-way light time, the time for a signal to leave Earth and reach the spacecraft, was about 18 and a half minutes. So we had to make the spacecraft really smart. And it had an onboard guidance system where it was able to take images of the asteroid surface, compare that to basically an atlas of the asteroid that we had preloaded into its memory, and it made its own maneuvers to target that very precise location on the surface, which is why our performance was so phenomenal.
TAG is NASA's shorthand for touch and go. Do we know how hard the tag was?
That's a really good question. So we know how fast we were moving when we contacted. We were coming in at 10 centimeters per second, which is pretty slow. It's kind of like a baby's crawling speed. And the asteroid appears to have just parted in front of us. Again, it looked like a fluid. One of the things that's really hard about these kinds of programs is you're in a different environment physically than we are here on Earth. In particular, the gravity, the force of gravity is incredibly low on the surface of the asteroid. So we hit a pile of gravel. Very much we could see rocks, about an inch or so all over the surface where we landed. But the surface just kind of flowed away from us, and that allowed us to penetrate very deeply into the asteroid and collect that sample. Our thrusters fired to reverse our motion and get away from the asteroid 6 seconds after we made contact, but we were still moving down into the asteroid for another 3 seconds before the thrusters had enough force to back us away and move us away from the surface of the asteroid. So the surface of the asteroid was really soft, and offered almost no resistance to the spacecraft moving in. One of my colleagues who's in the business, he wrote me with a very apt description. He's like, it's a good thing you fired your back away thrusters because it looked like you were going to fly straight through the asteroid. That's kind of what it was like moving through a cloud of dirt on the asteroid surface.
You mentioned it takes a little over a half an hour for a radio signal to travel round trip between the spacecraft and Earth at the spacecraft's current position. Does that time lag present any control challenges at this point in the mission?
Definitely today. So we talked about how we saw some of the sample that was leaking out of the collector. And as a scientist, it's breaking my heart because I know every one of those particles is a scientific treasure. So we directed the team to go for the stow operations on an expedited timeline, which is to take that sample collector, put it inside the return capsule where it'll be safe and no material will be able to leak out after that point. So we're doing real-time, like tele-robotic operations today, and it's excruciatingly slow. So, you know, we all got gathered here around 7 o'clock this morning. I'm still in Denver at the mission support area at Lockheed Martin. Been here for over a week now. So we commanded the TAGSAM arm to move into a position. And when we're losing material, it's kind of like a salt shaker. So if we stop moving, the material doesn't come out. But if we do any motion with the head, it's like shaking a little bit of material. So I'm like, okay, minimize the motions on the spacecraft, minimize the motions on the arm. We just commanded the spacecraft return capsule to open up, and we're getting ready to move the arm into the stow position. And all of this takes this 37 minute one-way light time. So we send all these commands, they travel across the solar system, the spacecraft does its activity, and then sends the data back to us with the images and the status that says everything went according to plan. So we're moving forward in kind of like hour to 90-minute chunks here. You know, we set up something and then we wait an hour or wait 90 minutes and we see what we got, and then we decide, do we want to move forward or do we need to change our plan?
Agony.
It's exciting. It's a different kind of operation for us, so that's always a challenge, but I am very much looking forward to seeing that sample collector safely inside the return capsule. I'll sleep a lot better after that's complete.
Oh, I'm sure. So what are the remaining milestones for the mission?
We got to finish this stow operation, so that's the #1 priority right now. Once that's done, we'll close the sample return capsule, and then we're getting ready to depart the asteroid. So we're going to be looking at plans for our departure maneuver. We got a few months. It's actually not until early 2021 that we can leave. So we still have some spacecraft activities, checkouts and things like that, just to double check, make sure everything is safe. It looks like it survived very well from the TAG event. And then it's a 2.5-year journey home. And so we're starting to think about those samples landing on Earth on September 24th, 2023.
Congratulations to you and the entire NASA team on this wonderful accomplishment. Where can we go to find updates about this mission?
Definitely our website, which is very easy to remember, asteroidmission.org. We put all of the latest images and all of the news up there. We're also on social media at OSIRIS-REx, all one word, on Twitter, Facebook, and Instagram. We have a YouTube channel where we put a lot of our videos out as well. That's also OSIRIS-REx. So we really hope that people can follow along with this amazing adventure.
Dr. Dante Lauretta, Professor of Planetary Science in the Lunar and Planetary Laboratory at the University of Arizona and Principal Investigator for the NASA OSIRIS-REx Asteroid Sample Return Mission. Thanks again for your time, Dante.
Thank you, Tonya.
And find more of my interviews right here or at tonyahall.net. Thanks for watching.